Hi everyone, in this video I'm going to talk about carbonate sediment. This is the sediment that makes the rock types limestone and dolostone from carbonate minerals like calcite and dolomite. Carbonate sedimentation is strongly tied to the activity of organisms like those in the coral reef shown here. Most of the organisms in a reef environment like this precipitate carbonate in some manner, and organisms are responsible for making most, if not nearly all, of the carbonate sediment produced in the modern world and in the rock record. For this reason, carbonates are often said to be born and not made. Most of the sediment deposited on Earth today consists of mudstone of some type or another. Carbonate sediment makes up roughly 16% of all sediment deposited on Earth today. And carbonate rock, limestone and dolostone, make up about 16% of the sedimentary rock record. That's roughly equivalent to all the sand and gravel sediment being deposited on Earth today and all the sandstone and conglomerate in the rock record. The 5% of other types of sediment are all other types of chemical sedimentary rocks that we'll discuss later. So carbonate sediment, volumetrically at least, is pretty important, and limestone and dolostone are pretty common sedimentary rocks. Carbonate minerals are those that consist of the carbonate anion, CO3, bonded to some cation or a combination of cations, and those would be the cations that are most common. The three cations that most commonly form carbonate minerals in seawater are magnesium, calcium, and strontium, and I've listed these in order of their ionic radius. So magnesium is a smaller ion than calcium, which is smaller than strontium. There are three basic carbonate minerals that precipitate in sedimentary environments. These are aragonite, calcite, and dolomite. They differ in terms of their structure, their composition, and also their solubility. Aragonite is orthorhombic, which means it's got a loose crystal lattice, and it's soluble enough that it's considered metastable, meaning that over geologic timescales it will convert to calcite. Aragonite cannot incorporate magnesium into its crystal lattice because magnesium is a small ion and the crystal lattice of aragonite is too loose to hold it. But it can incorporate easily the larger strontium ion in place of calcium. So even if aragonite converts into low magnesium calcite over time, which will happen, one can tell it was originally aragonite if it's got a high proportion of strontium in it. Aragonite is the most common primary precipitate of carbonate in the world's oceans today. Calcite is rhombohedral. It's got a tight crystal lattice. It comes in two forms, both of which can precipitate directly from seawater or lake water. Low magnesium calcite has low solubility, and thus is quite stable. And high magnesium calcite, or simply magnesium calcite, is more soluble than aragonite and will revert to low magnesium calcite over time. So both aragonite and high magnesium calcite tend to convert to low magnesium calcite given enough time to do so. Dolomite is an ordered magnesium calcium carbonate with a 1-to-1 ratio of magnesium to calcium. It's the least soluble of all of these and therefore the most stable. Dolomite can form from calcite under certain conditions that we will discuss later. Carbonate minerals originate in an aqueous solution that contains bicarbonate from weathering reactions on land. So when carbonic acid reacts with continental rocks during weathering, And there's the reaction to produce carbonic acid, which dissociates to a hydrogen ion and bicarbonate. And that is the origin of this hydrogen ion in a weathering reaction that we discussed earlier in class, the weathering of anorthite to kaolinite. Well, in order to keep this balanced, then, we would have to add that's HCO3, 2 bicarbonates to this side of the equation. And what this tells us then is that most of the water on Earth has at least some amount of calcium and some amount of bicarbonate in it. And those are the raw materials that we need to build carbonate minerals in solution. So the calcium and bicarbonate that are produced during weathering end up accumulating in oceans and lakes. And meanwhile, seawater, rainwater, and lake water will all react with the atmosphere to produce more carbonic acid. So this equation right here is the same as the carbonation reaction that we were putting up top. There's plenty of bicarbonate and calcium in the world's oceans and lakes to produce calcium carbonate. But that formation is inhibited in situations where there's excess carbonic acid. So if we look at the equilibrium between calcite, carbonic acid, and calcium and bicarbonate in seawater, we have plenty of this, and we have plenty of this to react with in most of the world's oceans and lakes. The only thing that's highly variable is how much carbon dioxide you're adding to that water. And it turns out that if you add more carbon dioxide, you get more carbonic acid, and that tends to run this reaction on the bottom to the right, which results in dissolving calcite or aragonite. If you instead remove carbon dioxide from the water column, then this reaction will run towards the left, resulting in carbonate precipitation. So as an example of this, carbon dioxide is also present in groundwater, both by interaction with the atmosphere and also interaction with plant roots and organic acids in soils. So groundwaters are typically highly charged with CO2 and therefore can dissolve quite a bit of limestone. When CO2 charged groundwater is traveling through limestone and ends up seeping into the roof of a cavern through either fractures in the bedrock or just through the bedrock itself, as soon as it comes in contact with the air in the cavern, it loses its CO2 to that atmospheric air where the concentrations of CO2 are lower. And as a result of that loss of CO2 to the air, it precipitates calcium carbonate as the dripstone formations that you see here. The rock type that forms dripstone is called travertine. Travertine is a type of limestone, just a general term for a type of limestone formed in caves or springs on land. There are several ways to remove carbon dioxide from seawater as well. In oceans and lakes, several factors can reduce CO2 locally and thereby favor the precipitation of carbonate minerals. CO2 is more soluble in colder water, which you can see from this graph right here. As temperature goes up, solubility goes down. CO2 is also more soluble under greater pressure. So as pressure goes up, CO2 solubility goes up. And that's simply because as you increase the pressure, you push more of that gas into solution. Finally, agitation of water by waves can physically knock gas out of a solution, including carbon dioxide. So we might expect that carbonate would be more likely to precipitate in warm, shallow, well-agitated waters where CO2 is being released from solution. And this is true. You can intuitively remember all of this by considering a carbonated beverage. The CO2 gas, to make the carbonation, is forced into solution at high pressure during bottling and then released when you decrease the pressure by opening the bottle or the can. If the can is warm, you're going to get a lot more fizz because more CO2 is being released because the liquid is warm. If you were to take that bottle or can and shake it first and then open it, it will fizz and release a lot more, sometimes to your great inconvenience. I mentioned at the outset that carbonate precipitation is tied tightly to the activity of organisms. Organisms have several strategies for precipitating carbonate and other minerals as well. But this general process is called biomineralization, and there are two main forms of biomineralization. Induced biomineralization involves precipitation of carbonate by microbes which produce locally favorable environments for carbonate precipitation around their cells. And as a result, these microbes get encrusted with encrusted with carbonate, and this can create intricate structures such as those in this stromatolite right here. This is a fossilized microbial mat that has undergone induced biomineralization as a result of the activity of microbes. Controlled biomineralization involves the organism intentionally building a structured carbonate skeleton, such as this coral, these seashells, and this coccolithophore. And they build these structured carbonate skeletons by both creating a favorable condition for carbonate to precipitate and by directing the form of that precipitation by making proteins that act as seed crystals for carbonate to precipitate around. This can happen both surrounding cells and also within cells, and can make intricate designs even at very small scales. So if you look at the scale bar right here, this is just 2 microns across, and this is a very intricate structure. When this structure disarticulates and these plates fall to the seafloor, they make a familiar rock type called chalk. Microbial mats can also bind and trap already existing carbonate particles in the water column by secreting a extracellular polymeric substance, or EPS, and this is just a fancy word for snot or slime. You can see it here, and that snot will basically trap any carbonate particles that happen to be in the water column around it. There are a few other factors in carbonate precipitation that we need to consider. In water that is turbid with detrital sediment, like the mud coming out of the Mississippi River right here, you'll get more mud deposition than you will carbonate. So even if carbonate is forming in the water column, the sediment that is deposited will be mostly detrital. This process is called masking by detrital sediment. So you don't actually get a limestone here. Instead, you would get a sediment consisting of some part detrital mud and some part carbonate, and that's called a marl. It'll fizz just like limestone, but it's not pure limestone because it may be mostly detrital mud. Clear water is incredibly important for the precipitation of most carbonate because many primary carbonate producers are photosynthetic, or they're symbiotic with something that is photosynthetic, so they need light to grow. Nutrient levels are important to facilitate this because high nutrient waters promote the growth of algae in the water column. And these algae grow quickly and can rapidly cloud the water, which will overwhelm carbonate producers like coral and reduce the visibility or clarity of the water and inhibit photosynthesis. Most coral reefs therefore grow in nutrient deserts. Finally, depth is important because lower depths have greater pressures and thus higher CO2 levels. The carbonate compensation depth, or CCD, is the depth in the ocean below which all carbonate dissolves completely. So from the surface of the ocean in the photic zone, where you may be producing carbonate, when that carbonate then sinks, it will sink through an area of the ocean called the lysocline. And in the lysocline, it will slowly dissolve as carbon dioxide becomes more and more concentrated in the water. Once it falls below the carbonate compensation depth, or CCD, it'll dissolve away completely. And the depth of the CCD is shown schematically in this map here. And from this, you can see that the carbonate compensation depth is shallower in colder water, deeper in warmer water, and varies in other less predictable ways around the ocean basins. Carbonate is produced in the oceans in two main types of carbonate factories. The pelagic, or open ocean, carbonate factory, shown here, is a produces carbonate at or near the sea surface in the open ocean. And then that carbonate that's being produced by things like plankton and sea surface algae, then once it's produced and once the organism producing it dies, that then settles down to the deep sea floor, although it can't settle down to the seafloor if it's too deep, because if this production's happening above a level of the ocean basin that lies below the CCD, once that carbonate settles to the bottom, it will have already dissolved. So this type of factory produces deposits like chalk and calcareous oozes, that are calcium carbonate deposits on the seafloor of the open ocean. And most of the production that makes those is taking place near the sea surface and then settles down. The benthic, or seafloor carbonate factory, produces carbonate right on the seafloor by organisms that are either rooted to the seafloor or moving about the seafloor in some way. That carbonate that's produced right on the seafloor is due to the growth of organisms, and also it can be reworked by waves and currents in the same way that detrital sediment gets reworked by currents and waves. So one of the biggest types of carbonate factory are coral reefs in the modern world. And this is the distribution of modern-day coral reefs, which are the most productive benthic carbonate factories. A reef is a carbonate buildup on the seafloor that is large enough to impede the passage of waves. So these are actually high points on the shallow seafloor, and they're built by organisms that produce carbonate. You can see pretty quickly that the world's reefs exist between about 30 degrees north and 30 degrees south latitude, and that's because the water here is warm. Reefs also occur only in shallow water, and in some cases the water is shallow simply because the reef has grown from deep water up to sea level. Reefs also tend to occur where the water is clear, and so you'll note that there are a couple places where you might expect to find reefs, but you don't because big rivers are putting a lot of sediment in the water, say around the mouth of the Amazon, the mouth of the Mississippi, the mouth of rivers like the Niger and the Congo in Africa, and so forth. Finally, tropical islands are great places for reefs because there's very little landmass to produce a lot of detrital sediment in the first place and to add excess nutrients to the water. And the water is clear, warm, shallow, and usually well agitated right around the edges of the islands. Benthic communities of carbonate-producing organisms can and do exist, however, in deeper and colder water, but they're not shown in this map, and they're not nearly as productive as these shallow water reefs are. The pelagic carbonate factory produces carbonate virtually everywhere on the sea surface, but that carbonate only accumulates in regions of the seafloor that lie above the carbonate compensation depth. So all of these red areas here are deeper parts of the seafloor that lie below the CCD, and therefore any carbonate produced on the sea surface will sink down and dissolve before it gets to the bottom. Carbonate produced by the pelagic carbonate factory also will only accumulate on the seafloor where there is little sediment input from from continents, which is shown here as terrigenous sediments. Finally, siliceous sediment tends to accumulate in areas of colder water, such as the circumantarctic region and the west sides of continents, which are, due to global ocean circulation, are colder water. The currents on the west side of continents are all headed from the poles to the equator at the surface. Okay, I put this slide up just as a reminder that carbonate sediment consists of allochems. These are the particles of carbonate sediment, and micrite mud. This is mud produced in the water column. And then carbonate rocks can be cemented together by sparite cement. We've already discussed how different types of allochems or carbonate particles originate. What we haven't really yet touched on is the origin of carbonate mud. There are three main ways that carbonate mud originates, and these are shown here. One is direct precipitation from the water column. Another is the disintegration of calcareous green algae that produce carbonate around them, and then when they die, that carbonate ends up spreading across the seafloor as mud. And then mechanical and biological erosion of carbonate sediment is a third process. Whenever carbonate mud is produced in a lake or a part of the ocean, it generates this phenomenon called a whiting. So a whiting is a discoloration of water due to the production of carbonate mud. It's unclear just how much mud, if any, is produced by direct precipitation from water, although it's theoretically possible and even probable that this happens. Documented cases of spontaneous precipitation of carbonate mud from water always seem to have another cause. For example, the spontaneous generation of carbonate mud that turns the waters of Lake Michigan white during the late summer months, and you can see the dates down here, and the gradual whiting of the lake, could be direct precipitation from the lake water simply because the water is getting warmer and losing CO2. But it could also be due to biomineralization by bacterial blooms that occur during those same months. Whitings in the Bahamas, like this, have been shown to be due to, in some cases, resuspension of bottom mud by fish, or the release of carbonate mud from the disintegration of calcareous algae like this penicillus here, which when it dies releases all of the carbonate particles that you can see just starting to accumulate on parts of it down here. As these penicillus grow, they become so encrusted with carbonate that they look like little snowballs on a stick. And then when they die, they release a cloud of that carbonate as mud into the water column. Carbonate mud may also be produced by different types of bioerosion by fish and organisms that burrow or bore into carbonate sediment, or by abrasion of other types of carbonate by waves and currents. One of the unique properties of the carbonate factory is that because carbonate sediment binds together so quickly, it can build upwards from the seafloor to make a raised platform, often even during sea level rise or during subsidence. Other types of sediment don't do this. Carbonates are really the exception. There are three main styles of carbonate platform produced in this manner: a ramp, a shelf, and a bank. And these three things are all very large-scale features. So we're talking up to hundreds of kilometers in size. Ramps and shelves are both attached to a landmass, such as a continent. So there would be a landmass here in that direction. Whereas banks are isolated. And so if sea level is here, you have a deep basin surrounding a carbonate bank all the way around. The edges of carbonate platforms may be rimmed or unrimmed by smaller buildups called reefs. Reefs are these buildups that are large enough or shallow enough to block incoming wave energy from the open ocean. So if you have a rimmed platform, all of the wave energy stops here, and you end up having a shallower water lagoon where the water is quieter. That is behind the rim, and that rim again would usually take the form of a reef. In an unrimmed platform, those waves can continue to travel unimpeded all the way to the landward side of the platform. Other types of buildups do occur in deeper water. This type of buildup shown here would probably most likely be called a mound. A mound is a carbonate buildup on the seafloor that does not reach high enough to impede the passage of waves. The different types of carbonate platforms that you find on the left may evolve through time as shown on the right, where we see first a ramp that evolves with continued deposition and continued subsidence into a rimmed shelf, and then continues to evolve into something that is looking more like a carbonate bank, or at least a series of pinnacle reefs. So what's happening in this progression of three diagrams is that we have, from left to right, differing amounts of carbonate precipitation. So there's a high precipitation taking place in this area, lower off towards the basin, lower off towards land. If carbonate precipitation continues to be high towards land and in this reef area, then we will build up a shelf. Carbonate precipitation dies down as you head off to the basin. And then finally, if we end up having isolated areas of high carbonate precipitation surrounded by areas of lower carbonate precipitation rates, we can get something like these pinnacle reefs or a carbonate bank. So there's a couple different types of reefs, and again, reefs are much smaller features than platforms. They can be part of a platform or independent of one, but the typical definition of a reef is a carbonate buildup that reaches near enough to sea level to impede the flow of waves. A fringing reef is one that fringes the shoreline of an island or the shoreline of a continent. You can see all along this reef the waves are breaking. That's why we have whitewater there. The reef itself is this darker area here, and then there's some other reef buildups towards land, and they are fringing this island. These are most typically found surrounding islands like in the image shown. If an island like this were to subside to the point where it falls below sea level, what we'll be left with then is an atoll. An atoll is basically a fringing reef that has continued to build higher and higher even while the island that it surrounds has sunk below sea level. So if we were to draw the underwater structure of this atoll, what we would see is that the atoll has simply built up and kept pace with the relative rise in sea level in this location, even as the landmass that it used to be attached to is now submerged. Pinnacle reefs are just localized buildups that grow fast enough to keep up with the subsidence of the basin that they're in or with sea level rise. This is a pinnacle reef surrounded by divers. You can see for scale it's not a very large feature. And finally, barrier reefs are, that term is restricted to a type of reef that grows on the shelf edge surrounding a continent. And these are generally the largest types of reefs, and they are one part of a very, very large platform system, a shelf platform system. Reef builders today consist of corals and algae, but in the past, so here's today, in the past we've had lots of different types of organisms that have built reefs. For example, rooted clams, such as these shown here, have been reef builders in the Cretaceous. Sponges and phyloid algae, things called stromatoporids, archaeocyathans, and even microbes have built reefs in various times of Earth history. And so it's just important to recognize that what we think of today as a coral reef is not necessarily what you would find in the rock record, because there have been many different types of reef builders in Earth history. So let's look at two different types of modern carbonate platforms. On the left, the Great Bahama Bank sits detached from all surrounding land masses, and it's a zone of shallow water that you can outline pretty clearly. And it's surrounded by much deeper water. And I won't continue to outline that anymore. I think you get the idea. This carbonate bank has built up to 4 kilometers of relief with respect to the surrounding seafloor. So the depth of the ocean here is about 4,000 meters, and the depth here is tens of meters in the bank. And if you were to swim out to right here, you'd essentially see a 4,000 meter cliff going right down to deeper water. The waters surrounding the Bahama Islands, and here's one of them, this is Andros Island, are quite shallow and produce quite a bit of carbonate. The Bahama banks have been growing upwards for about 100 million years, since a time when this part of the Atlantic was still in shallow water. And since then, the Atlantic has subsided, and the banks have just simply grown along with that subsidence, and the subsidence has been slow enough that the upward growth of the platform in this area has been able to keep up with it. On the right-hand side is the Great Barrier Reef, which is an example of a rimmed carbonate shelf. The shallow water shelf is attached to the continent of Australia, and the reef, the rim, is separated from the continent by this shallow water lagoon here. The rim is fairly continuous, and it forms a barrier to deep ocean waves, so waves will end up breaking here and only get through the reef in a few reef passes. Reef growth along the barrier is promoted by that agitation from breaking waves and by the shallow, clear water that occurs at this distance from the continent. Smaller, less continuous patch reefs occur within the lagoon, but most of what you would find in this lagoon is carbonate mud. The light colors in both of these images indicate sedimentation of that carbonate mud in the shallow water protected areas of the platform that are sheltered from waves by islands or rims. Here's a map showing the type of sediment that's produced in different portions of the Great Bahama Bank. Green is grainstone, and it's pretty easy to see that most of the banks consist of grainstone, and this is because most of the banks are unrimmed by reefs. The only places that are protected from waves coming in from the open ocean are those that are associated with islands, such as the Andros Islands here, and places that are protected by reefs. Where you have these rimmed parts of the carbonate bank, you shelter certain areas of the bank from incoming waves, and these are the areas where you can produce wacky stone and pack stone, such as here, sheltered by Andros Island, and other places in the banks sheltered by reefs. These types of sediment, pack stone, wacky stone, and just mudstone, accumulate in deeper waters away from waves. So say here off the Florida coast, there's Florida. And lastly, oolites or oolitic grainstone tends to occur at the ends of deep inlets, such as here, at the end of tongue of the ocean, where the tides come through and produce enough agitation, but not too much agitation, to continuously rework the sediment and coat it in carbonate. Here's a model of an arid climate carbonate shelf showing where different types of carbonate features would be expected to occur. The barrier reef is a skeletal structure that occurs right on the edge of the shelf and grows up high enough to block wave energy. This skeletal structure would consist of boundstone made by corals, made by algae, and so forth. Boundstone would also be found in these algal mounds and in these patch reefs. Mud mounds are the result of trapping of carbonate mud by organisms like seagrass, which will basically trap all, or that microbial snot, which act as baffles to impede the flow of mud through them. Much of the open platform interior is probably wacky stone or pack stone. So all of this area here would be fairly muddy. Grainstone would be found near the reef, either where waves are breaking stuff up and washing it over the reef, or breaking pieces of the reef and shedding it this way, or within the reef itself. So all that grainstone would be composed of skeletal fragments mostly, produced by organisms living within the reef. And a mixture of mud from suspension mixed with sediment gravity flows or even rock falls would exist on the shelf and then further out in the basin. So the basin floor out here would be largely carbonate mud, and in some areas you may deposit carbonate sands delivered out there through things like turbidity currents. Okay, well that's it for carbonates for now. Thanks for watching.